Good evening to all and welcome to the another session of the NPTEL course Heat Transfer. So today is our 10th session. So today we'll be discussing about the contents that are related to the week 10 topic, which is the basically the continuation of week 9, the radiation part. So today we will be discussing some of the practice problems related to the contents discussed. So let's have a brief recap. So in the last week 9, just introduction of the radiation heat transfer. So in this week 10th lecture, we the Kirchhoff law, then the absorptivity, emissivity, that kind of topics were discussed. So we solve some problems related to that, and we will just start with the first question. Okay. So we have a consider an opaque surface whose spectral hemispherical absorptivity varies with wavelength, and the distribution, spectral distribution of incident radiation is also shown. So I will draw the figure. So you have to determine the total hemispherical absorptivity of the surface. So the required figure I have drawn. So you can just start solving this out. Okay. So the first is the graph between absorptivity and the lambda. So this is E lambda, which is 4 meter square. Okay, so these are the given figures. Yes, this is the uh, hemispherical means this distribution of the absorptivity with wavelength is the first figure, fig 1. Okay. And the fig 2 is the spectral distribution of incident radiation. Okay, so these are the two figures which are given. So we have to find out what is the uh, total hemispherical absorptivity of the surface. I will give you some time to solve this out. So
Excuse me, sir. In the second figure, E lambda should be G lambda because it is not, it is the incident radiation.
okay, you can take, because here it may be assumed from a black body, so you can consider G also. So if you start somewhere, you can tell I will start solving. Okay, so what is the total hemispherical absorptivity? Total alpha. This is what it is asking the question. It's like level 0 to infinity alpha lambda g lambda incident b lambda, which is integral 0 to infinity incident. Okay. So this is the uh, expression for total absorptivity. What is this integral 0 to infinity g lambda d lambda, which is the incident radiation, right? Total incident radiation. So how we can calculate this?
By calculating the area under the
Yeah,
second curve.
yeah, we can do it by considering the area under this curve. So which is half into, so that we can, if you divide this into three regions, the first part is a triangle, so half into 1.4 into 3006, 36,000 plus, then it's a rectangle kind of thing into 2000 plus again a triangle. So did you got this answer? What is this answer? Can you please calculate and say?
So 144,000.
1 double 4. Can you please check because I am getting 126,000. What is this first part? Can you calculate this? I will calculate.
So can't we take 36,000 common and then we can calculate?
Yeah, you can calculate. You can do whatever they want. It should be finally it will be same.
So 126,000.
Yeah, 126,000.
Yeah.
Yes. No, watt per meter square. So this is the total incident radiation over the entire spectrum. So now we can easily find out alpha, which is equal to. So basically, the alpha is divided between zero point 0.7 and uh, sorry, between up to 1.8. This alpha is 0. So we need not consider, like if you multiply, even if you consider it will be 0. Like okay. So the first part, that is 0 into to 1.8. Up to 1.8, the lambda value is 0. Okay, from here. So g lambda I d lambda divided by 1000 plus. Then it is constant for the entire spectrum. Means it is constant, that is 0.7 for lambda greater than 1.8. Okay, but so up to this much, right? There is no absorptivity. So we have to consider the irradiation from this lambda value. Okay, that is 0.7 into, now from here to here it's a constant like 1.8 to 3.4 g lambda I d lambda divided by plus 0.7 into integral 3.4 to infinity, oh sorry 5, it is g lambda I d lambda divided by, so this part is 0. Okay, so which is equal to 0.7 into, so just area up this much area, what is it is 3.4 minus 1.8 into 3000, that is 6000 plus 0.7 into this area, half into 5 minus 3.4 into, that is 6000 divided by, can you please calculate and say what is this alpha value?
Point 48.
Yeah, the answer is 0.48. This is the total hemispherical absorptivity of this surface. So I hope if you are given any profile like this, so it need not be, so it can be a different profile, like say from 1.8 to some 3.8, it will be, say it is 0.7, then after that it is uh, zero point 0.8, like that. So you have to divide this region accordingly and find out the uh, total absorption. So let's move on to the next question. So this is also a continuation of the first part. So if the surface is diffuse and it is at 1200 Kelvin, okay, what is its total hemispherical emissivity and determine the net radiation heat transfer from the surface. For solving this, you may need this black body radiation function table. So I hope you have this. So can you try or I should start solving?
Sir, if the surface is diffused, then emissivity should be 1 because it is black body, isn't it?
No, 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 no. You shouldn't confuse diffuse body and black body. That are different. Diffuse body in the sense it doesn't the intensity or the emission doesn't have any spatial variation. It is not black body. Diffuse bodies are not black bodies.
Actually, sir, some reverberation is coming in your sound. Your sound is not clear today. I don't know
Hello.
what the reason. Your sound is not clear.
Yeah, can you hear me now?
Yeah, now it is clear.
Ah, so all black bodies are not diffuse. Like, or diffuse bodies are not black bodies. So you should understand that. If in diffuse bodies there is no variation with respect to theta, the intensity is not like it is not it is not independent of the spatial orientation or the theta value. I think you should make it clear. So for a diffuse surface, I will give a hint. For diffuse surface, alpha lambda will be equal to, so the emissivity and absorptivity will be same for that particular level, which means this profile of absorptivity and emissivity with respect to lambda will be same. That is the hint for solving this question. You're asked to find out the emissivity. So I think I already explained about this in the last class. How? So now you got the emissivity map. Is my voice clear now?
Yes, sir.
Okay. Anyway, I will start. So the emissivity value or the emissivity map will be almost is the same as that of absorptivity. So like uh, so the first one is the emissivity, total emissivity. Total emissivity is integral 0 to infinity E lambda EB lambda at particular t lambda divided by integral 0 to infinity EB lambda d lambda. Okay. So this is simply we can express it's the black body EB. EB at that particular temperature. Okay. So EB at that temperature is equal to integral 0 to 1.8, because 1.8 it's 0 into E lambda, sorry, into infinity 0.7. So this part becomes 0 and this is like zero point 0.7 times the black body radiation function. I hope you remember. F infinity to 1.8. So which is we can write it as 0.7 into black body radiation function from 0 to infinity minus black body radiation from. So what is from 0 to infinity? Black body radiation function. actually there is no need of looking at the uh, table also. It's one, right? So all I already discussed the last class. One minus the only thing you need to find out is this function. So lambda one t is equal to how much? Uh, Lambda one is 1.8 into t is 1200. So this will come out to be so. So can you please find out what is the black body radiation function corresponding to this? I hope you have that map. Otherwise, you can see this. So this will be in between this value. So you can extrapolate, sorry, interpolate, and it will come out to be around. You can do that at a homework 0.094. I hope the method is clear how to find it out.
Yes.
So, yeah. So can you find what is this answer?
Point 0.63.
Yeah. 0.634. So the next part is we have to find out the net radiation. Okay. So the net radiation is some part what in the body, some part of the some part is incident that let it be G. Okay. And some part is getting absorbed that is like uh, and sorry, some part is getting absorbed and some part is getting what reflected. Okay. And assuming there is no transmittivity, so some part is coming, some part of radiation is coming, some part is getting absorbed and some part is getting reflected. Okay. and and some part is, and because of its temperature some emission is there, that is EB. So the net radiation is the one which is emitting, okay, plus the reflected part, that is rho g, minus the incoming part. Okay. So this is epsilon sigma t raised to 4 minus what is this? This is alpha g. It is which is like alpha plus rho is equal to 1. So uh, rho minus 1 is equal to minus alpha. Okay. So can you please find out what is this answer? Q is equal to, so the emissivity we already find out, which is 0.6342 into epsilon. State 4 minus alpha is 0.48 times the total. Can you please find out what is this answer?
68.5. No, 68,516.9. 68516.9.
Actually, I am getting a different answer. Okay, you can verify it. I'm getting 14.09 kilowatt per meter square. Okay, you can just verify later. So I hope the method is clear.
Sir, one thing is not clear to me that G is the incident radiations and rho G is the reflectivity.
Yeah, not
And this
reflectivity, reflected radiation.
yeah, reflected radiations.
Yeah.
And EB is the emitted.
Because of its temperature. Because of its temperature. Yes.
So what is the difference that it is radiating and it is reflecting and minus G you are writing? Then where what is this difference indicating?
If difference in the sense which this one.
No. That EB plus rho G minus G.
Ah,
What is this indicating? Where these radiations are going? What is the where is the difference? Is it
net,
accumulated?
it's the net radiation. How we consider a net thing of an object. Whatever coming in minus whatever coming out, or coming out minus coming in. I hope it is clear. So some part of radiation is coming in, and some part is reflected, and it is emitting some energy because of its temperature, which is the emissive power.
So, sir, what about the absorptivity? Is it absorbing some of the radiations of G also?
Which one? Yeah. That's how finally come out to be rho g. So finally come out to alpha g. That is what it is absorbing. What is this rho g minus g?
But sir, this the radiations that EB, which is the emission,
Ah,
emissive that radiation which it is emitting at temperature T.
ah.
So won't there be any rise in temperature when it is absorbing?
It will rise. I'm not what I'm saying. What is the radio? It is emittive. No, some radiation. Whether it is what is the value of this? Is positive. So the temperature actually it is radiating or it is losing energy.
Okay.
It is some part is radiating. Okay, that is dominant, but some part is coming. So the net, what is the net difference? Just like accumulation, say for example, if I have a tank and some 10 kilogram of water is coming to the bucket or some tank, and 20 kilogram is leaving, and it has some energy, or it has some already some uh, uh, volume it is there. So the what is the net mass flow rate? So 10 is the net mass flow rate, which is dm by dt.
Okay, sir.
Yeah. So let's move on to the next question. So we have a small solid metallic sphere which has a opaque diffuse coating for which the uh, absorptivity is given, which is 0.8 for less than 5 micrometer and 0.1 for greater than 5 micrometer. And the sphere, which is initially at a uniform temperature, of 300 Kelvin is inserted into a large furnace whose walls are at 1200 Kelvin to determine the spherical absorptivity of the coating for the initial condition. It's almost similar to the first question we have done. I will just start solving. So we have a furnace. Okay, so this is a furnace enclosure which is at some temperature T of furnace which is 1200 Kelvin, and we have a small metallic board. So small in this it is given because the size of this small is very the ball metallic sphere is very small as compared to the furnace. Okay, so this is the sphere. So since the furnace surface is much larger than that of the sphere, the irradiation approximates emission from a black body, which is the Kirchhoff law. It's already discussed in the lecture. So this whatever is the irradiation that is happening, that is coming to this body, that is alpha, or this is whatever G it is coming. Okay, irradiation it is coming. It is approximated. It is approximated as an irradiation from a black body, which is at a TF, that is the temperature of the furnace. So we are assuming it because the size is very small as compared to the uh, size of the sphere is very small as compared to the furnace. So this is the same approximation we have taken for during derivation of the Kirchhoff law. Okay. So what is the absorptivity? What is the that is integral 0 to lambda alpha lambda g lambda incident. Okay, d lambda divided by 0 to infinity g lambda I d lambda. Okay, so as this irradiation is approximated to be from a black body, we can say E lambda is equal to EB lambda. So E lambda at that temperature. Okay, TF temperature should be also there. So G lambda at TF to be equal to the same from the black body radiation of the surface, which is equal to E lambda B, or at which is the furnace temperature is 1200 Kelvin. Okay, so that is the thing we think that we have to do here. So we can rewrite the alpha. It's integral 0 to infinity alpha lambda E lambda B lambda at that temperature integral 0 to infinity E lambda B lambda E lambda. Okay. So ask this how to what is the variation of lambda with respect to variation of alpha with respect to lambda up to up to how much up to 5 micrometer is 0.8, then it is 0.1. Okay, so this is the given information. So we have to split this into two regions, that is so integral 0 to 1 point lambda 1. I am taking this as lambda 1 alpha lambda 1 E lambda B lambda 1 lambda lambda divided by integral 0 to infinity e lambda b plus integral 0 to uh, lambda 1 to infinity. This is alpha lambda 2 e lambda b. This is similar to our black body radiation function, which is like, because I can take alpha lambda 1 outside this integral. Why? Because over this 0 to lambda 1, this absorptivity is same. Like that, it is same for lambda 1 to infinity. So I can take that out of the integral. So finally, it will come out to be alpha lambda 1 f, which is the black body. Inside this is the black body radiation function plus alpha lambda 2. It's like 1 minus I hope you understand how the 1 comes, because f0 to infinity is 1. So 1 minus f0 to lambda 1. So basically what you have to find out is what is f0 to lambda 1. Okay, so what is lambda 1, which is 5 micrometer. So lambda 1 T is equal to what is the temperature? 1200. So 5 into 1200, which is around 6000 micrometer Kelvin. So can you find out what is this value? Yeah, it's given. So this is directly given. It is 0.7378. Okay, 0.7378. So you can directly put alpha lambda 1 is 0.8 into 0.7378 plus zero point 0.1 into 1 minus 0.7378. Can you please calculate this?
Point 0.62.
Yeah, it's 0.6. So this is the total hemispherical absorptivity of this small ball. So next question is also a similar kind of question, which is the total emissivity of the means coating. It's like over the ball, it's a coating. It's already given. So what is the total hemispherical emissivity of the coating for this initial condition? Initial condition, because it's specified, because initially the furnace is at 1200 degrees Celsius, and what is the temperature of the ball? It's 3000, sorry, 300 Kelvin. So under this condition, what is the total hemispherical emissivity of the ball? So how to find this? As it is mentioned, the coating is diffuse. Okay, it's an opaque diffuse coating. So what is the, if we specify diffuse coating, what is the relation between the it's monochromatic emissivity and this absorptivity for diffuse surface? I already told this in the previous question. What is the relation? Since the surface is diffuse, plus epsilon emissivity, monochromatic emissivity will be equal to the alpha lambda monochromatic absorptivity. Okay, so this is the key we have. So what is the E at of the sphere Ts? Okay, equal to integral 0 to infinity E lambda E lambda B lambda Ts. Okay, now it's the temperature of the, it's the emissive power, emissivity we are calculating. So now it's the ball, it is the one which is emitted by the, we are interested in the emissive power, okay, of that ball which is at that temperature, initial temperature, which is Ts. So here Ts is equal to 300 Kelvin. Okay, d lambda divided by integral 0 to infinity E lambda B lambda Ts. So equal to, actually, what is the relation? Means, as it is same, we will get the same profile for the point 0.8. This is 0.8, 0.1, 5 micrometer. Okay, so this I am E lambda 1 and E lambda 2. So Ts is equal to integral 0 to 5 E lambda 1 E lambda B lambda. What is Ts? Which is 300 Kelvin. Infinity 300 Ts E lambda plus integral 5 to infinity lambda 2 lambda 300 divided by E lambda B lambda 300 D lambda. Okay, so as it is same, we can take, means, for this interval as E lambda 1 and E lambda 2 is constant, we can take this outside. So E lambda 1, so what is this function? That is the black body radiation function. Okay, F0 to lambda 1 plus E lambda 2 1 minus F0 to lambda 1. So only you need to, what you need to find out is 0 to F, the black body radiation function, which is from 0 to lambda 1. Okay. So now I have to, can you please tell what is lambda 1? What is the product of lambda 1 and T we should take? Can you please find out what is lambda T, which is used, which we need for finding out the black body radiation function? Just the product.
So 1500.
Yeah. So lambda 1 Ts, which is 5 into, so sorry, just say 300, which is 1500 micrometer Kelvin. Can you please find out what is the F0 to lambda 1, which is F0 to 5, black body radiation function? So, so it will come in between this. So you can just interpolate and find out. I'm just giving the answer, which is 0.014. Okay, let's check if it is between that. Yeah, 0.014. So can you please find out the answer? That is, one is 0.8 plus zero point 0.1. Can you please find out the answer?
0.91,
Point.
91,
Can you please post it?
0.11.
Yeah. 0.1. So this is the emissivity value for the board for the initial condition. So say I'm just asking. So at steady state, what will be the value of emissivity? When the ball attains steady state? Say for example, so I am keeping the 300 Kelvin board inside a 1200 Kelvin furnace. So what happens to the temperature of the board?
It will rise.
Yeah. So it will rise, and till how much value it will rise, and when it will stop?
Then it will become equal
Yeah.
with the
So when it will become equal to the surface temperature of the furnace, which is 1200. Okay, that is the steady state. So now there is no change in the temperature. So whatever it is receiving, it is emitting. So under that condition, what should be the relation between alpha and, so what should be, so the alpha should be, what should be the total emissivity and total absorptivity value?
both should be equal, sir.
Yeah, it should be equal. So it should be equal to the alpha, which is we already found it out, which is 0.62. Okay. So if the question asked like this, there is no need of calculating this value. You can directly write the alpha is equal to epsilon is equal to 0.62. So how we can say, because at final state this TS will be TF. So, so whatever black body radiation function we are calculating here, it is similar to here. So both value will come out to be same. Okay. So that can be another type of question. So if a steady state, what will be the emissivity value? So now we will move on to the U factor finding. So we have a circular tube of equal length and diameter, which means D is equal to L, okay, or L or H. Yeah, I will write it as H here. Okay. So we have to find out. So the surfaces are naming. This is one surface, that is top surface of the cylinder, and the bottom surface is named as 3, and the curved surface is named as 2. Okay. So we have to find out the view factor F22. I will give some time. So I will join within through 3 minutes. So by the time you can try. I hope the question is clear. Is there any confusion? Okay. Have you got the answer?
Sir, surface 2 is a plane, sir. No, it is not plane.
It's not plane, it's a cylinder, a circular thing. So you need more time or should I start?
So just 1 or 2 minutes.
Okay, fine. Okay, I will start. So it's already given d is equal to, that's a diameter is equal to height, which is the height h. This is like a cylinder, and f1 to 3 is given. That is from this surface to this surface, it's given 0.17. We are asked to find out the f22. So by the rule of few factors, 1 plus 3, f21 f21 plus f22 plus f23 should be equal to 1. That means From if you from the radiation from this second surface will fall on to first surface, second surface, and as it is curved, it will, some part will follow it into itself. And if you see as d is equal to h because of the symmetry, whatever part of radiation is going to here, it will go to here. That is like a symmetry. If the surfaces are symmetry, or the shape is symmetry, f f21 should be equal to f23. Okay, so it will come out to be f22 plus 2 times f23 should be equal to 1, and f22 should be equal to 1 minus 2 f23, which is equal to 1 minus 2 times f21. Okay, so this is what we need to find out. So a1 f13 is equal to a3 f31. So either we have to find out either f23 or f21. Okay, so a1 f13 is equal to a3 f31. So f13 plus f12, that is from 1 and 1. So f11 will be 0, or there will be some part.
F11 will be 0, sir.
Yeah. So and that I am not writing, otherwise I am right. So this will be 0. So it should be 1. So f12 will be equal to 1 minus f13. Okay. So f13 already given, which is 0.17, which is equal to 0.83. Okay. So now we got f12. Okay. So if f12 is given, we can easily find out what f21, because by reciprocity theorem a1 f12 is equal to a2 f21. Okay, so f21 is equal to a1 by a2 by f12. So what is a1? This, that is pi by 4 t square. What is a2? Pi d times h, that is the height, into f12 is 0.83. So pi cancel, and d and h are same, right? So it will become d square. So that will cancel. So 0.83 divided by, it will become 4. So it will come out to be 0.2075. Now we got what is f12. Okay, f21. So just substitute back in this equation. So the required is f22, which is 1 minus 2 times f21 is equal to 1 minus 2 into 0.2075. Can you please calculate this?
0.56.
Yeah, it will 0.58, I think. So this like view factor finding is like we have to do some uh, mathematics, or it's like a mix of algebra and visualization. You have to think in which direction, if we go, we will get the view factor. So it's like an interplay of this summation theorem and reciprocity theorem. So you have to practice a little bit to be convenient with this view factor finding. Okay. So you can, if you take any textbook, you will get a lot of old examples of finding this view factor. You can just try this out, like a sphere on a sphere, and sphere on a cylinder. This kind of it's generally commonly asked questions related to view factor. Okay. So this is also a view factor thing. So consider a infinitely deep wedge of equal length at an angle alpha. Determine the view factor between them when alpha is equal to 90 degrees. So first let we will derive the view factor. for any arbitrary angle alpha. Okay. So let the wedge we look like this. I hope you know what is a wedge. It's like a, so it has infinite depth into the plane of the paper. So this is it is equal. So let it let this is the alpha angle alpha. Okay. So we will derive for any angle alpha, and then we will apply to the at 90 degree. Okay. So these two are let it be L1 and L2 means. So I'm deriving for general case. Okay. So if assume it may be helpful for you, because if always it's useful to derive. So L1 and L2, I'll say for example, and it is at an alpha. Okay. So this is what we have. What is a view factor we have to find out. So I'm closing this by considering another imaginary surface. This is like this is atmosphere. Okay, this wall. This is wall is atmosphere. I'm taking this length as x. So there is a rule known as triangle rules. Triangular rule for which is basically used for triangular enclosure. So any triangular enclosure having of sides A, B, C, A of sides say A, B, C, then a view factor FAB is related as A plus B minus C divided by 2A. So like A to B, A plus B minus the third side divided by 2A. So this is general. Say for example, if BC, can you please say in the same way how it will become? B plus C minus A divided by 2B. Okay. Like that, you can find out A and C also. So this is a triangular rule for this is a rule for triangular enclosure. So this like derivation you can find it on any textbook. So here you are fast to find out between any points, like if A and B, I am taking considering this as A phase and B phase. Okay, and this is C phase. So if A to B, which is basically if B and C, you can find it out like that also. B plus A plus B minus C by 2A. So this is A is L1 or L2 plus L1 minus C is X divided by 2L2. So here L1 is equal to L2 is equal to L. Say I'm assuming it as L. So FAB is equal to L plus L minus X divided by 2L, which is equal to 2L minus X divided by 2L is equal to 1 minus X by 2L. Okay. So what is this? So this is a if this is a right angle triangle. Okay. This is C. So this is right angle triangle. So what is sine alpha? Sine this is alpha by 2. Okay. So this is alpha by 2. What is sine alpha by 2? Can you please find out? X by 2. So as is in iso means it's like the L1 and L2 is same. It will be alpha by 2 and it will be x by 2, x by 2 the both sides. So it will be x by 2 by L. Okay. So I'm just replacing that here. FAB is equal to 1 minus sine alpha by 2. So this is the view factor for a wedge. Okay. Having equal sides and at any angle alpha. So put alpha is equal to 90 degree. So FAB is equal to 1 minus sine 45. What is sine 45? This value
1 by square root 2.
1 by root 2, which is equal to, it will come out to be 0.293. So for example, what is if alpha is equal to 90 degree? What is FAB?
No, at alpha
So
90 you are talking
alpha is equal to not 90, alpha is equal to 180.
it
If
will
alpha
be
is
1.
if alpha is equal to 180, then side 180 by 2 is 90. So the side 90, sine 90 is how much?
1.
Yeah. So then FAB will be 0. So what is the case of like 180 degree alpha? This is like this. Okay. So it's like it's not facing each other. So there will be no radiation that is emitted by this going to fall on this. So, so the view factor will be 0. I hope you understood how it becomes 0.
Yes, sir.
So this triangle rule, you heard before or you already know this?
No, sir, I was not knowing.
Yeah, you can just refer a textbook. It's already given. So it is easy for you to solve this kind of triangular enclosure problem. If you there is nothing to remember in this. If you have the sequence, if you got the sequence, you can write instantly what is FAB. Okay. So let's move on to the next question. So we have a 5 into 5 cubical furnace shown in the figure. Okay, whose surface closely approximate as black body. So the base, top and side surface of the furnace are maintained at uniform temperature as shown in this figure. Okay. Determine the net rate of radiation heat transfer between base and side surfaces. This is what we have to find it out. So between the base and the side surfaces means, so this is the base. Okay, this is the top. So can you say what is uh, which heat transfer I should find? Whether it is Q13, Q12, which one I have to find out.
But sir, this net heat transfer will always be from this top surface. So
Okay,
how?
that's fine. It's like you have to find out. This will be also interacting because this is 800, this is 500. So you cannot say that there will be always net heat transfer from, yeah, if you consider this will be emitting to this and going to this also is going to this. So how to find out if the sides will decide and say if you go in the right direction, if it is positive, which means the surface one is emitting heat.
No, sir, but it is a cubicle, so there will be symmetry and it will be always from top.
Okay, that's fine. I am asking from 1 to 3, that is the I am asking net rate of heat transfer between base and side surfaces. From here, from the, this is 800, this is 500. So there will be a net heat transfer from here to here. Are you agreeing with me or not? Because of this temperature difference.
What about the other surfaces? They are not.
Other you forget now. It's asking about between this and this only.
Then there will be radiations.
Yeah, radiation only. Yeah. We are not. We are not talking about conduction and convection. It's only radiation. Yeah.
Conduction will be there, but if there is air, then the radiation, then convection will also be there. If
Don't neglect that. We are talking about radiation only here.
yes, and then there will be heat at bottom to the side.
Yeah. So we have what is asked in the question. We have to find out what is Q13. So that is from bottom to the sides. What is the net radiative heat transfer? Can you please move? Yeah. So what is Q dot 13 net radiative heat transfer? It is A1 F1 to 3. This is the view factor times sigma T1 raised to 4 minus T3 raised to 4. So what we have to find out here is only F13. Okay. So that is our task because other things are
What
given.
about emissivity, sir? What about emissivity?
It's asked to assume black surfaces. Then emissivity is 1.
Okay, sir. Okay.
So we have to find out F13. Okay. So what is we cannot directly find out F13. So what is F11 plus F12 plus F13 which is equal to 1. So what is F13? Sorry, 11.
F11 is 0.
Yeah. So now F12 there is if there is I don't know whether you are aware of these kind of charts. So there are specific charts for view factors. You can, if you are using some heat transfer data books, you can find it out. And also in all the heat transfer textbooks, you will find this kind of charts. So if you are able, if you are given this kind of charts, you can easily find out the view factor. So here, not to find out F13, if I get F12, I can easily find out F13 because so F12 here is here in this according to this chart, A1 is equal to A2. Why? Because it's a square. Okay. And L1 is also equal to L2, which is equal to D because it's a square. So the ratio L2 by D will be what? It will be 1. Okay. And this L1 by D is also 1. So you have to map 1 1. So this is the 1. Okay. And you have to find out where is the L by D 1. So this is the L by D 1. So the intersection point is here. It is around 0.2. Okay. Not around 0.2, it's exactly 0.2. So we got from this chart here what is F12 is equal to 0.2 from chart. Okay. So like this, there are means charts for view factor, charts for parallel disk of same size, different size, like that. You can just look into the textbook. So now what is F13? 1 minus 0.2, which is equal to 0.8. Okay. So what is Q1 to 3, which is A1 is 5 into 5, which is 25 meters square, into 0.8 F13 into 5.67 into 10 raised to minus 8 into 800 raised to 4 minus 500 raised to 4. So this will come out to be around 394 kilowatts. So have you means earlier seen this kind of charts? Familiar?
Yes, sir.
Okay, then there is no need of much explanation. So this in the next question we have to find out the net rate of radiative heat transfer between the base and the top. Now between this one and two. So now it's very easy because what Q1 to 2, which is equal to A1 F1 to this is black body T1 raised to 4 minus T2 raised to 4. So F12 we already find it out 0.2. So A1 is 25 square, sorry 25, 5 into 5, zero point 0.2 into 5.67 into 10 raised to minus 8 into uh, T1 is how much? 800 raised to 4 minus. So this will come out to be minus 1319 kilowatt. So you see, so if our direction or if our way of doing is fine, automatically the sign will correct. So what is meant by negative? So we assume that the radiation heat transfer is taking from 1 to 2. But by getting the negative sign, we say that the direction is reversed. So the heat transfer is taking from 2 to 1. Now I think you get got clear. If you consider 2 to 3 also, it will be negative. So 2 to 3, it will be positive. If you consider 3 to 2, it will be negative.
Yes, sir.
Okay. So next is the radiation heat transfer from the uh, net radiative heat transfer from the base. Okay. So what is the net radiative heat transfer from base? Heat transfer from base. That is Q dot 1. That is it comprises Q11 plus Q dot 12 plus Q dot 13. This Q dot 11 is 0 because F11, the the view factor F11 is 0. So this Q dot 12 and Q dot 13. Q dot 12 is minus 1319 plus Q dot 13 is 394, which is positive. So minus 125. So now your assumption is right. Okay. Now I proved that there is a net radiative heat transfer the from this one. Okay, which means some part, some radiation is coming from top and some radiation is going to this side. But this coming part is more than the leaving part. I hope you got it. So that's why the net radiative heat transfer from the base surface becomes negative. I hope that side got clear.
Yes, sir.
So this will become more clear when we do radiation network problems maybe in the next class. Okay, how this sign will become more important there. So another question of view factor, we have a solid cylinder which is located in the center of a hollow sphere. The diameter of the sphere is 1 meter while the cylinder has a diameter and length of 0.5 meter each. We have to find out the view factor F11. So now I think you are a little bit comfortable with view factor. So I will give 2-3 minutes to solve this question. If you have any doubt regarding the question, you can ask. Did you got the answer? So we have a solid cylinder which is located at the center of the hollow sphere. Okay. We have a hollow sphere which is regarded as surface 1, and we have a cylinder. Okay. The diameter of the sphere is given. So the radius of the sphere is 0.5 meter. The diameter is given 1. And the cylinder diameter and the length is cylinder diameter is 0.5, and the length is also 0.5. So D is equal to H is equal to 0.5. So we are asked to find out what is F11. So F11 plus F1, so this entire surface, a solid cylinder, we are taking it as 0.2. Okay. F12 is equal to 1. So F11 is equal to 1 minus F12. If you find out F12, we can find out this one. Okay. So A1 F12 is equal to A2 F21. Sorry. Yeah, right. So what is F21? Can you say?
Sir, that for that I was looking at the table.
There is no need of table. You can just check whether any part of 2 uh, will come if you write F21 plus F22 is equal to 1. Okay. So F22 will be what? 0. Because of we are considering the outer curved surface. So none of the radiation from 2 will fall on 2 itself. So that part is 0. So F2,
Okay, so
F21.
that will be taken as convex.
Yeah. So
Okay.
F21 is 1. So whatever radiation that is emitted by this cylinder will go to 1 only. Okay. So F21 is equal to 1 because F22 is equal to 0. So now F12 is equal to A2 by A1 times F21, which is equal to A2 by A1. What is A2? That is 2 top and bottom, that is 2 times pi by 4 d square plus the curved surface, that is pi d h. What is I have taken h, the whole divided by what is the curved surface area, that is 4 pi r square for sphere, 4 pi r square. Okay. So if you calculate 2 into pi by 4 into 0.5 the whole square plus pi into 0.5 into 0.5, 0.5 into 0.5, the whole divided by 4 pi into what is the radius? Diameter is given 1, so radius is 0.5 square. So this will come out to be around 0.375. Okay. So now what is it's now there is nothing to find out. We already know. So F11 is equal to 1 minus F12, which is equal to 1 minus 0.375 is equal to 0.625. Okay. So that's what I told you need for view factor finding. You need some kind of visualization also. You have to think in how uh, the radiation can emit. Okay, the convex surfaces, concave surfaces. You have to think of little. Okay, we will move on to the last question. Consider an evacuated two-dimensional quadrilateral enclosure as shown in the figure. So we have to determine the FAC for the quadrilateral. Also determine FAC if all the four sides of the quadrilateral are equal. So you can use the triangular method that I already discussed in the previous question. Okay, I'll give you to some 2 minutes to just try this. How you can use triangular method? You can just divide this section, okay, into two triangles, and you can apply. Then you can do some arithmetics, and then you can finally find out what is FAC. Okay, so if I imagine F F sorry, FAA plus FAB plus FAC plus FAD is equal to 1 because of the summation rule. So what is FAA?
That is 0.
Yeah, that is 0. So what we are asked to find out is FAC, which is equal to 1 minus FAB plus FAD. Okay. So I am dividing this into two different types of triangles. This is L1. I'm connecting its diagonally. It is L2. Okay. So the view factor relationship for this FAB, if I write this triangle, okay, this this triangle, it's comprise A, B, and because we have to find out AB, okay, then AD. So AB, if I write FAB is equal to A plus B minus C divided by 2A. What is the third side, which is L2? So A plus B minus L2 divided by 2A. That is FAB. So for AD, I am considering this triangle, that is AD and L1. Okay. What is FAD? A plus D. Sorry, this we cannot write because the C is, it will be confusing. So A plus D minus the third side, which is L1 by 2A. Okay. So just substitute this here. FAC is equal to 1 minus FAD, sorry, AB plus FAD. So this is equal to 1 minus A plus B minus L2 by 2A minus A plus D minus L1 by 2A. So if you rearrange something, it will become by 2A minus A minus B plus L2 minus A minus D plus L1. Okay. So this will become L1 plus L2 minus 2A. Sorry, that A will be cancelled out because here it is minus 2A plus 2A. Then minus of B plus D. Okay. So I'm taking the minus common divided by 2A. So this is FAB. Okay. So this is FAC. Sorry. This is FAC. That's a general equation for FAC. And that is our first question. Determine FAC for this configuration. Now, if all the sides of the quadrilateral are equal, which means it's a square, which is I am writing A is equal to B is equal to C is equal to D, which is equal to say X. Then all are X, right? So then what is L1 and L2 in the according to this case? This is root 2x, right? Because the Pythagoras theorem, if you apply. I hope you understood how I got root 2x.
Yes, sir. Yes, sir.
Yeah. Next, just substitute this value. It is FAC is equal to L1 plus L2 minus B plus D divided by 2A is equal to L1 plus L2 is root 2x plus root 2x minus x plus x2x divided by 2x. Okay, which is equal to 2 root 2x minus 2x divided by 2x, which is equal to root 2 minus 1. So which is equal to 0.414. Okay, so this is how. So I hope if you are given a rectangle also, you can, this is the general uh, equation. So if it is a rectangle, you can find out the L1 and L2 in that direction, that is root of this. It will become little bit complex. You cannot directly find it out. Okay, you will arrive at an expression, a simplified expression of this. So, okay, so now let's we come to the end of our session. So I hope this session was helpful for you and you learned something new out of it. So, okay, thank you for joining the session and see you the next week, Monday.
Okay, sir.
Next
Thank
week.
you.
Thanks for joining. Thank you.
Okay, sir.